this video we're discussing how to find Nash equilibria under incomplete and imperfect information. Even in extensive form games with imperfect information, we may still be able to find Nash equilibria relatively easily. The simplest case is when the player has a dominant strategy in the information set. So here in the example on the right, player 2 will play Go because it is a subgame perfect choice in both nodes of the information set. On the left, playing Go yields a payoff of 6 for player 2 instead of 4 for playing Stay, and in the subgame on the right, playing Go yields a payoff of 3 instead of 2 from playing Stay. Given that player 2 will play Go for sure, player 1 will play Left. So left Go is the Nash equilibrium of the game and 5, 6 the equilibrium outcome. Why does the equilibrium only have 2 strategies in it? Because, although the second player has 2 decision nodes, these 2 decision nodes are in the same information set and there is only 1 strategy per information set. If the player has no dominant strategy in the information set, we may be able to rewrite the game into a normal form game and find the Nash equilibria this way. For example, here we can rewrite the game on the right in matrix form, look for the best responses and see that there are no Nash equilibria in pure strategies, which means we need to find the mixed equilibrium. We know one exists because there always has to be at least one Nash equilibrium in every finite game. We find the mixed Nash equilibrium by setting the expected value of each strategy equal. We find that player 1 is indifferent between playing left and right if Q is 6/7. Remember, Q is a probability that player 2 plays Go instead of Stay. And we find that player 2 is indifferent between playing Go and Stay when P is 1/2, which is the probability that player 1 plays left. So the mixed Nash equilibrium here is 1/2 left, 1/2 right, 6/7 Go, 1/7 Stay. If the imperfect information comes from a move by nature, we can just use expected values. Here in this game, player 1 makes a decision, then there's a coin toss, and then player 2, unable to observe the result of the coin toss, has to make a decision between T and G. In the first subgame, playing T gives player 2 an expected value of 2.5, and playing G gives an expected value of 5. So this means player 2 plays G in the first subgame, and in the second subgame, playing T gives player 2 an expected value of 8, and playing G gives an expected value of 6.5. So player 2 plays T in the second subgame. This is what player 1 can anticipate. So player 1's expected value of playing left is 8.5, and the expected value of playing right is 5. So the subgame perfect Nash equilibrium in this game is left, G, T. So far, we have assumed that the players are risk neutral. What do we do if the players are risk averse? Well, if the players are risk averse and the payoffs in the game are not given in utility, but they are given, for example, in money, then we first need to turn the payoffs into utility. So let's assume here that both players have the same utility function and that this utility function is square root of x. So for every payoff, we calculate the square root and then replace the original payoffs with the utilities, and we recalculate the subgame perfect decisions. So in the first subgame, the expected utility of playing T is 1.5 and the expected utility of playing G is 2. In the second subgame, the expected utility of playing T is 2 and the expected utility of playing G is 2.5. And since player 1 anticipates this, the expected utility of playing left for player 1 is 2.5 and the expected utility of playing right is 2. So the Nash equilibrium now is left, G, G. So dealing with players who are not risk neutral is not particularly difficult. We just need to turn the payoffs into utilities using the utility function first. All these examples so far have been examples of imperfect information. Examples of incomplete information are player 1 does not know player 2's payoffs, like this, or player 2 does not know the probabilities of nature's move, or player 1 does not know whether player 2 is risk neutral or risk averse, or player 2 does not know whether player 1 has selfish or non-selfish preferences, or player 1 does not know whether player 2 maximizes expected utility or plays something like maxi-min, and so on and so on. In games with incomplete information, players need to form beliefs about the information they do not have, usually about the other player. These beliefs assign probabilities to what type the other player may be. For example, the type may be risk neutral or risk averse. Because these type of games rely on beliefs and probabilities, these games are called Bayesian games. Bayesian games are defined by the n players, the action space, which is essentially the same as a strategy space, the payoff functions, the type spaces, so all possible types, so for example risk neutral and risk averse, or risk neutral, risk averse and risk seeking, or maybe specific utility functions and so on. And the beliefs, which assign a probability to each possible type, representing how likely the player's beliefs these types are. We can even find Nash equilibria in these Bayesian games. They are defined as a combination of strategies that maximize each player's expected utility given their beliefs about the possible types and the play that results from them. Now, we're not actually going to do this because this is rather complicated, and this is something you may, for example, see if you take advanced game theory later. As you can imagine, unless we have a very simple game, this gets really complicated, especially if we include higher order beliefs. What are higher order beliefs? Higher order beliefs are what players believe the other players' beliefs about them. So for example, if player 1 believes that player 2 believes that player 1 is rational, even though player 1 may not actually be rational. If we're taking these higher order beliefs into account, there really is no end to it, because if you believe that the other person believes something about what you believe, then the other person needs to form beliefs about what you believe, the other person believes you believe, and so on and so on. It never ends. However, this is just to tell you that these things exist. We're not actually going to analyze them in detail. However, you should have some idea what a Bayesian game is. A game with incomplete information, where players form beliefs about the relevant information in the game they do not possess.